I'm not in charge. I'm the one who's going to start.
Oh, you're going to start right now. Oh, okay. Nice to meet you. So nice to meet you. I had a question, not to derail our conversation too. I just wanted to check that the top slides display your name.
So you see the guy, the big guy in the back?
You want in the corner?
There's the mic.
Yeah.
This is the
Okay, I'm going to check that you're here. Nice to meet you. Yeah, thank you for the invitation. We didn't even recognize each other at all.
All right, good morning. It's a really great pleasure for me to welcome you all to this morning for this RDMI Research Data Management Implementation 2017, we call it. I'm really pleased to see so many people able to make it. I was actually getting worried with the weather that we'll miss a lot of people, but the people made it through really are brave. I would like to really thank you for that. So I'm Birali Runesha. I'm from the University of Chicago, and I'm the chair of the RDMI 2017. And I wanted just to take a few minutes to kind of tell you a little bit the motivation and what brought to get together here. This workshop is actually a follow-up on a workshop that actually started in 2011 at Princeton on research data lifecycle management. And in 2013, and that was the time when data management was being announced and becoming kind of a requirement. In 2013, we decided to have the first one in collaboration with CASC, and it was also an NSF funded. And then at that time, it was still new, there were less tools, and then many universities, we did not know what to do. And then last year, I started among a couple of my peers, say, it's been 4 years, and there's been a lot being accomplished, and people are still trying to achieve more implementation, but yet on our campuses, we are still struggling with the same questions. Basically, the service layers were still not really keeping up with all the tools and even leveraging everything that is available out there. So let me see, okay. So when you look at the research data lifecycle, starting from the time where a faculty will generate data from an experiment or simulations, all the way to publication. So you see a publication, you see results in a publication, but a data point in that publication may be a result of 4 or 5 years of research that we do not even know how to collect, how to trace. So if I'm sharing data, what am I sharing? Am I being able to have access to that data? So it really brings a lot of questions that the huge amount of data that our faculty are generating are really creating a lot of complex questions that the faculty or the researcher or the graduate student is not equipped to address, or is not even aware that the tools that they need are available out there. So what we tried to do back in 2013 and previous workshop, and I have to acknowledge, beside those 3 that I just mentioned, there's been numerous other workshops that are really relevant, and all of them touching different aspects. But all of them trying to see what are we able to do to leverage to solve the same question of research data management implementation. So what did we do? We tried to bring different people from community, and I come from more of the research computing side of things. But when you talk about data management, we also have to work on our colleagues in the library, for example. And then many campuses have been trying to even work how our services can work together to serve our faculty. So we said, why don't we bring all those community together? There are also out there people in the industry and other leading experts, other organizations that have been working on these same questions, to get together to kind of to reflect a little bit on what has been accomplished to date. And there are still many challenges. and then to see what those achievements, how can we make sure they become in as a service to be able to be aware. But I think more importantly, and you're going to hear me emphasizing this tomorrow, is what do we continue this discussion to kind of talk about these opportunities moving forward to provide contributions even to those who are developing tools, that these are being the effective tools that, because each discipline, as you may see and you're going to hear throughout this day and tomorrow, require different tools, require different services. So the impact of the workshop, it's kind of narrowed it down a little bit to the impact RDMI is having on the research, and then also trying to encourage again this whole concept to work with partners and community, because the community has to drive what gets implemented, and then also the broader impact. So what we did for you guys got, everybody probably picked up a copy of the agenda. The way we structured the agenda for this workshop is a little slightly different from the one in 2013. We're going to have 3 panels, which means we're going to have some of the community-focused conversations, and then within them we're going to have the breakout sessions. So those panels have been kind of structured. The first one, and after having one of the keynote, actually we talked this day, today, we selected actually the role RDMI, for example, is playing in the reproducibility of science. I think that's really a topic that we're hearing quite often, that to be able to really reproduce, you got to have access to the work that the previous other people have done. But the first panel really kind of focused on what is happening on the campus. So on the campus, we want to hear from a faculty perspective. What are the challenges from that faculty? What are the examples from a faculty point of view? And then we will move on to a representative or somebody who represents a research computing center, because those are the service provider, and then hear a voice from a library, and as well as a voice from a minority serving institution. And then after that, we're going to have a breakout session, and we will notice you have tables with numbers. The way we did this today is to have small group of people, and there are going to be questions where you're going to be discussing. Hopefully we can go through all those 3 questions. We will have like a table lead, but we would like to ask a volunteer per table who will be able to summarize at the end for 2 to 3 minutes, and I was told 2.5 minutes. And then so that at the end we can have kind of a summary of that. So we have 3 of those. And then the next day we have selected some RDMI initiatives that we're going to hear some presentation. These are basically really exemplar, and we had a tough time here actually selecting, but the people will be talking in that particular group just going to kind of give us that view of things and activity that be happening. And then we have another one for the industry, because when you talk about long-term preservation, are we going to do this in the cloud? Are they going to be in premises? So it's really important to hear people on that, and then so on. And the next day, day 2, we're going to have the funding agency's perspective, and then and again with another breakout session. So the only thing I want to also acknowledge here, that all of this has been possible. It couldn't have been possible without the help of my colleague in the planning committee. We work almost every 2 weeks. We're on the phone constantly, and I don't know how much I can say. Thank you to all of you for the help you provided, and some of my staff at Chicago, Kim, Lela, and Marissa, that really were able to do all this logistical. And I want to acknowledge some of our sponsors, the National Science Foundation. They've been gracious to make this possible, Microsoft, Globus, and Mozilla, CASC, and the University of Chicago. So I'm going to stop here because I need to show an example, keeping on time. And it's really a great pleasure for me to introduce Amy Walton. She's been a big supporter, and for introductory remarks. Thank you.
Well, Thank you for those kind words, Birali. And to all of you, welcome. Thank you for coming. Just a couple of key points that this is an important topic, and this is a very timely workshop. And just basically there's about 3 reasons for that. Is that, as Birali mentioned, for the past 5 years, cyber infrastructure development within particularly the academic community where National Science Foundation operates has been developing capabilities and addressing challenges based on some guidance we had received from the national academies in a very large set of studies that were under the umbrella of cyber infrastructure in the 21st century was the title of that set of guidance, or CIF 21 as you get into acronym land. But what they also do is they provide guidance with the understanding that technology changes, problem changes, challenges change, and they usually, after 5 years, they put in a sunset clause. That guidance is sunsetting. So we at NSF are looking to see now what are those key challenges, what are those key issues, what do we do next? So you are here at an excellent time. Many of you have provided research advances in those 5 years. I see many familiar faces. Welcome there. But there's also new challenges and new institutions that can help answer them, and I welcome all of you as well with that. So one thing to note is that we're more likely to make intelligent decisions as we go forward if we can measure things. So and if we can sort of understand what the key problems are, how to measure the problems and the progress that we're making. So you folks have a treasure trove of possibilities, and we look forward to hearing what you have to say. You'll be totally shocked to know that the quantity of data is increasing rapidly. And it's growing rapidly in every field. Some of the disciplines that we worked with in the past that didn't use very much data for the studies that they did are now, 10 years later, using and building on data sets that are larger than the leaders in astronomy and places that have had a lot of data in the past are now, they have exceeded those kinds of usage rates. So everybody is using data. I had the privilege of working for quite a number of years with NASA, with some of the original data that the rovers were bringing back from Mars and visualizing and those kinds of things. But remote sensing is no longer the purview just of satellites. Is that the bottom line from that is we are all astronauts now. Every one of you has a smartphone that exceeds the capabilities of all the Voyager technology that is out there. All of your wearables, all of the feedback that you get in educational feedback, the visuals that we're getting today. There's a huge amount of data, and there's tremendous challenges and questions to be addressed. Is that like those astronauts 40 years ago, we don't even know what, in a lot of areas, how we would measure that and what we would do next. But there's growing challenges that require inputs from fields that didn't exist at the start of our process. So welcome to all of you with this workshop. You all bring perspectives that we really need to keep answering those big questions. In the same way that data is, the quantities of data that we build upon are growing rapidly, there's another trend that NSF's budget is not growing rapidly. You're also shocked to hear that, I'm sure. But that the key issue for us has been that we at NSF are the one organization that basically works with and represents the 4,200 colleges and universities in this country. So there's a huge pool of knowledge and rapidly developing capabilities and research in that world. But in the future, there's also a lot of colleagues outside of that traditional area that we can draw upon. 2 generations ago, a good chemist that prides themselves on their work ground all of their own chemicals. Is it that you knew it was pure and you knew it was what you needed if you did it yourself? And I think in some ways, the scientists of today that pride themselves on, I need to be sure that I have done it. Well, there's a large community in the same way that the chemical industry now has, it's almost an ecosystem of capabilities, is that there's companies that know how to get you the purest chemicals or can help you acquire the data that you need. Instrumentation folks, there's a whole lot of capabilities that are out there. That's true now basically of every science, engineering, and education field, that there's a lot of teammates that we need to start, or at least be sure that we continue to collaborate with. And representatives from many of those places, from industry, from in our case, the publishing community, are here today. And of course, many of some of the institutions we currently work with that have new questions that are being answered. There's new research fields that are developing every day. So again, new teams are forming, new possibilities are going on, and that's one of the places that NSF does like to do, be involved, is at the front end, what are some of the new questions and how do you start to answer them? So we will be very interested in what you have to say. So I guess to summarize is that there's new challenges and new questions that are showing up every day. There's new options and technologies for addressing them and answering them. They don't always necessarily come from traditional places. So new opportunities, new industries, new capabilities are developing. And there's new voices that are out there. That's one of the nice things about working with NSF, is that every year there's a new stream of people in our community bringing in new ideas and new issues. So I guess just the bottom line, thank you very much for taking time out of your busy schedules to come and provide us with some guidance at this time that it would be very timely. During the next couple of days, today and tomorrow, you'll see many of my other colleagues, actually my boss, also named Amy. This is for ease of appellation. But she had headed the NSF activities in how do we deal with data and publication in the future. We'll be here tomorrow as part of one of the panels. I have, I think, some other colleagues that it's sort of, I need my eclipse glasses to be able to see if they're here right now, but I think that if you see any of us with an NSF badge, please don't hesitate to come up and introduce yourself, and any questions that you have. I could take questions if you'd like now, or maybe that's the best venue, because I think what we do need to do is to get moving with the topics that you've been asked to address today. They are very timely, and thank you.
Thank you, Amy. I see what you mean about the lights. Hello, my name is Wendy Kozlowski. I am a librarian at Cornell University. I work in the area of data curation, and I have been asked to be the enforcer at this meeting. So I'm here to attempt to keep us as much on time as possible. I do have a few brief announcements just before introducing our keynote speaker. First of all, we are recording these sessions, so we want to remind people of 2 things. Please, if you can help it, not walk directly in front of the camera. And when it comes time to ask questions, please either stand up and use the microphones, or we can be walking around and hand people microphones. So please wait to speak until you have a microphone. Some other busy work, if you are a person who uses Twitter, please feel free to use our hashtag. We encourage that. It's RDMI 2017, one word. The bathrooms, if you have not yet found them, outside of our door to the right are the closest bathrooms. There is also coffee outside as well as Starbucks downstairs in the main lobby. If you have questions throughout the meeting as far as logistics are concerned, please feel free to find me or Kim. Don't walk out that door. Wave your hand. This is the other woman in the back who knows where everything is. So please feel free to ask us any questions. And with that, it is my great pleasure to introduce our keynote speaker, Dr. Victoria Stodden. Thank you for coming. Dr. Stodden is Associate Professor in the School of Information Science at the University of Illinois at Urbana-Champaign, with affiliate appointments in the School of Law, the Department of Computer Science, the Department of Statistics, the Coordinated Science Laboratory, and the National Center for Supercomputing Applications. She is also faculty affiliate at the Center for Information Research in Science and Scholarship in the School of Information Sciences at the University of Illinois. Thank you so much for coming.
Well, thank you for the introduction, Wendy, and it's a real pleasure to be here. I'm very much looking forward to chatting with you. So today, one of the things that I wanted to try to do in my talk is really think about things where computational systems and architecture start to interact with notions like reproducibility. So what I was going to try to do was trace that story a little bit for you with a clicker that does not work. Okay, so I can ad-lib the talk. Okay, here we go, great. So maybe what I'll do is I'll just request for the slide to move forward. Okay, so I wanted to start thinking about the term reproducibility and maybe unpack that a little bit. As was mentioned in the both sets of opening remarks, actually, reproducibility is an issue that is talked about broadly and widely now, which I think is fantastic. But if I asked everybody in the room, I bet people would have very different definitions of what they thought comprised reproducibility. And I think a lot of it depends on what your scientific background is or what your professional background is and how you think about how people carry out research. So what I'd like to do is sort of maybe put some definitions and framing around the term that will help us sort of operationalize the discussion. And then I wanted to move to a discussion of some of the ways that I think cyber infrastructure and computational tools are not only able to enhance reproducibility, but actually are vital for supporting steps towards reproducibility that the various communities are actually taking. And then I wanted to conclude with some thoughts about where all of this might be leading, so sort of being a little bit futuristic and thinking about, well, what are we actually producing as a research community, and how is that making our scholarly record and our outputs actually look a little bit different and enable different actions on this scholarly record? Okay, if we could go to the next slide, please. Okay, so next one, I'm just going to unpack reproducibility for you. So if we roll back time and we think about what are we doing as a research community, one of the places we could start thinking about this is Merton's norms that he produced in 1942. Now, they're not without controversy, but I wanted to put them up here because I think sort of an overarching frame of my discussion today is how do we sort of stay true to scientific norms as we take on these challenges like, for example, reproducibility, like the development of computational infrastructure and its use across all sorts of different types of research. So the one that I'm going to pull out and focus on is the last one, skepticism. Scientific claims must be exposed to critical scrutiny before they will be accepted by the larger community. So if we could jump to the next slide, please. So this is a photo of Robert Boyle, and he is responsible for the notion that reproducibility is an important part of scientific research. So he developed this concept and actually had it ingrained in how we communicate scientific research in the 1660s. So this is something that he put forward this idea that scientific claims that are being made need to be able to have property that they could be independently verified by other people in the community. So prior to his innovations in scientific communication, you would be writing letters or meeting with the person who made the original discovery in order to try to understand how to do that work. And so he managed to impose this level of abstraction in the communication of science that would sort of decentralize, in a sense, how the knowledge that produced the innovations would actually be communicated. Okay, so transparency in the communication of the research process, this was where this cornerstone started, right around where we started journals, actually, in the 1660s. And that was part of the transactions of the Royal Society and how they started to structure the scholarly record itself. Okay, next slide. I think people in this room know most of what's on here. I put this slide up here just to concretize these ideas. I think a lot of the issues that we're grappling with around scientific research processes and how to instantiate them and then how to disseminate the research findings that come from these new processes are actually a result of us as a community taking advantage of all sorts of new technology. So the first couple of points there, yeah, we've got a lot of big data. People have sort of noticed that. So we're dealing with huge amounts of data, not just in scale, but in enormously different types of data. So for example, extremely high dimensional data is something relatively new for research methods and discoveries. We're coupling this with independent enormous advances in computational power. So of course we're able to do far more deeper and more far-reaching simulations and very sort of highly powered computational research to ask new, unique questions of our universe, of the world around us, as we're able to do these simulations, change a parameter, redo the simulation, and really try to understand the world and ask questions in a new way. So I think both of those are kind of well-established concepts. The one that I think is just as important and doesn't seem to be as well established is that now, with big data, you've always got code accessing data. And with computations, naturally, we're writing a lot of code to do these computations. You have deep intellectual contributions to scientific advancement that are appearing only in the software. And so this isn't software as sort of an implementation, sort of separate and overarching research ideas. This is really software as a first-class vehicle with deep scholarly contributions embedded in the software. Now, the reason I mention that is because, of course, software is still not routinely shared when it travels with or underlies scientific findings. So now we have this sort of medium or locus of contributions to scientific thinking and discovery sitting in software and largely unexposed still. Okay, so here are my couple of claims. So my claim is almost all of our scientific contributions and discoveries today have some computational component in them. So when I'm talking about computational science, I don't mean, really big systems or sort of heavily architected systems that are making computational discoveries alone. I do mean that. But also I mean a researcher who maybe did a survey or has taken some observations in her lab and puts them in Excel and starts to do some statistical tests on them in Excel. So there's an entire range of sort of scale in terms of how computation interacts with that research discovery pipeline. And I think all of it is important and part of this conversation. So we have this computational component appearing all over the research landscape. So that's my first assertion. The second one is, now that we have this computational component as part of our, sort of a routine part of our research, we have a mismatch in terms of how we disseminate the research and Boyle's and Merton's old standards around transparency, the ability to verify the claims, and also to enable that norm of skepticism. So we need to, I think, rethink how we communicate findings that have a computational component as part of how that discovery was done, and think about what the dissemination process actually is. If I could have the next slide, please. no need to go back a slide, but if you notice on the previous slide, I just wanted to mention Lior Patchter was there. I just grabbed a screenshot. And what he's saying in his keynote there on YouTube is how software contains ideas that enable biology, for example. So I just wanted to mention I'm not the only one who's noticed the importance of software as a vehicle for communication of ideas that are a basis of our scientific discoveries. Okay, so now to unpacking the notions of reproducibility. So I have found it useful to think about reproducibility in three ways. The first one I called empirical reproducibility. And I have a couple of slides on each of these just to sort of flesh out the definitions. Empirical reproducibility, I think of that as Boyle's version of reproducibility. So we have empirical experiments, say you get in a lab and you actually do some work in the real world, not in the computational world, and then you want to ensure that those experiments are reproducible independently the way Boyle envisioned. I compare that with statistical reproducibility. So if I'm extracting information or signal from a data set, I'd like to see that information replicate in new samples. So what have my statistical techniques done to ensure that it's actually a finding that's coming out of the data set? It's not some artifact of the data or the noise or the structure that is not actually something that's going to replicate in different situations. Finally, I like to sort of partition off computational reproducibility. So thinking about how can I ensure that these computational steps that were taken in order to get to the finding that I'm asserting and the claim that I'm delivering to the community, how can those computational steps be exposed or verified independently, thinking again about Boyle's vision for how we communicate science, exposed independently to the larger community. So what would that comprise? What would that look like? We saw in both opening remarks some hints around what could be components like the data, for example, software steps, workflows, and so on. So the rest of my talk will focus largely on computational reproducibility. So if we could go to the next slide, please. Thank you. So empirical reproducibility. So I am going to have just a quick slide to illustrate what I mean by that point. So there's two panels here on the left, sorting out the facts. This was a two-page report that was written and published in Cell Reports in 2014. And the story there, and I highlighted the part that is totally unreadable by you, so I'll just summarize it. But the part that I highlighted, these two labs had a grant from NIH. It was a lab at Harvard and a lab at Berkeley. And in their proposal, what they said is they were going to take 2 months at the beginning of the project, and they would reconcile the processes in the two labs to ensure that the cell output for their research didn't have some kind of signature or trace that would allow someone to identify which lab produced it. And the reason they wrote and published the report is it actually took them 2 years to reconcile the processes in the two labs that would allow people to, not be able to determine where that particular sample came from. And the difference was, I'm not a biologist, but if I understood the article correctly, was one lab at one point physically stirred a beaker with a sort of stirring stick. The other lab, the way they carried out their processes is at that point they would put that beaker in a centrifuge. And so that was enough to make a difference in the cell output for their research. And like I said, it took them 2 years to sort of peel back the covers on their processes to ensure that these results from the two labs were comparable. On the right, I put a screenshot of a National Academies workshop that also took place actually in 2014. And these are reproducibility in the context of where you have animals in a lab. And I just put it up there, one, because it illustrates my notion of empirical reproducibility, but also I think it illustrates another point, which is reproducibility is not costless, right? We might think about it in the computational context as sort of a power drain or resource drain if you're using machines or equipment to run code and so on. But some fields have a even more, potentially more serious problem. If you're reproducing results and that requires you to sacrifice animals as you do it, it's not clearly an obvious good to be consistently reproducing all these studies all the time. For example, there are certainly real costs associated with it. Okay, if we could have the next slide. So statistical reproducibility, so things here that I think fall in this category are all the issues around statistical methodology as it's applied to data discovery problems. So there are issues here, I won't go in detail in all of them, but just to flag some, people have heard the p-hacking debates around the use of p-values and generation of p-values for asserting whether or not a finding is a significant finding or not in a data set. Reporting standards, how have you actually prepared the data for analysis? What did you do with your outliers? How did you merge data sets and decide when records matched and so on? All of these kind of what seem like small decisions in your entire research pipeline can have very big impacts on the significance and the findings that you actually have in the data. So we have all sorts of questions in statistics that, if we haven't taken care of them, can affect whether or not you're likely to see that purported finding in a new sample or in a new experiment and so on, which is of course what we would like to see. Okay, the next slide, please. And I'll just make a sort of a footnote to that last slide, which is in 2014, Science Magazine issued new author guidelines to address issues of statistical reproducibility. So they did a variety of things. So submissions now to Science since 2014, you need to tell reviewers and editors what your data handling plan was. So reporting things like your decisions around outliers, your pre-processing, the preparation of the data sets themselves. Justify your sample size. So too small a sample size, as we all know, means that there's probably more uncertainty around any findings that you may have found in a very small sample size. Have you treated your samples randomly? Were you, as the experimenter or the author, blind to the conduct of the experiment? So you report on all of these issues now in a concretized way. And they also ensured that more statisticians were able to review the papers coming through the science publication pipeline. So those are concrete and specific responses that happened to what I'm calling my notion of statistical reproducibility. Okay, next slide, please. So for computational reproducibility, where I will situate the remainder of the talk, I think about aspects of computational reproducibility right back to the scientific method itself, and trying to think about how we would sort of interleave computation in all its various facets and digitization into scientific discovery, which of course is predicated on the scientific method. So traditionally we've had two branches of the scientific method: the deductive branch, so mathematics, deductive logic, and so on, and the empirical or inductive branch. So of course, if you want to do something like predict the floodplains of the Nile so you can plant crops appropriately, deductive logic is only going to get you so far. You need to be able to start doing things like inductive reasoning to predict where you might actually see sort of future flows. So there's been lots of talk, and I imagine people in the room have heard this kind of talk about how technology is bringing about new branches of the scientific method, a third branch of the scientific method around large-scale simulations, a fourth branch of the scientific method around data-driven discovery and computational science. So I snuck in a little question mark after branch 3 and 4, so I will come back to that question mark. If I could have the next slide. Okay, so I wanted to just give a couple of examples of these notions that have been around for quite a while now about third and fourth branches of the scientific method. So I just sort of Googled, and this is one of the first hits, so this isn't meant to kind of pull out anyone in particular. There's lots of this stuff on the web, but on the left you see, as you can tell from the HTML, a workshop from 1995. And this is a NIST workshop on modeling and simulation. Now, what was interesting to me about this description is right at the sort of workshop overview, they say it's common now to consider computation as a third branch of science besides theory and experiment. And of course, theory and experiment, they're referring to the first and second branches. And it's common in 1995. So this is something that's been asserted in some communities for a very long time. On the right, there's a co-edited book with fantastic chapters from many different authors. And even if you look in the preface of this book, The Fourth Paradigm, it says, this book is about a new fourth paradigm for science based in data-intensive computing. So they're sort of, embedding themselves in this idea of a fourth branch of the scientific method. If we could get the next slide. Okay, so now I wanted to take a step back and I want to come back to that little question mark that I put after third and fourth branch, and thinking about why we have a scientific method and what it really is that distinguishes scientific discovery from a variety of other activities we might do, such as visiting computations on a data set, for example. So the reason that we do it is because we obviously don't know the answer. This is part and parcel of discovery, is that we're not trying to get towards the solution in the back of the textbook. We're out in, new territory trying to understand new facets of our world that we don't know. And doing so means that we might make mistakes. Every step we're doing is sort of a new method or a new research discovery process leading to that new finding. And so what we want to do with the scientific method is, first of all, recognize that error can creep into that discovery process at any point, and then in turn try to convince the community that we've done everything we can to root error out of that discovery process. So our likelihood that the discoveries that we're presenting to the community are correct is as high as I can make it when I actually deliver them to the community. So this is very much in line with Boyle's original vision. So for the deductive branch, we have a very well-defined concept of the proof. You wouldn't present a mathematical claim to the community without detailing the proof that actually makes you think that that's a new claim to be delivered. Similarly, in the empirical branch, we have an entire machinery of hypothesis testing and appropriate statistical methods in a very structured way that we would communicate that work, the research around prediction from controlled experiments. So if you try to, submit an article and you leave the methods section blank, they won't even read it, right? The methods section is really important for understanding what it is that was done to get to those results. Why? Because we want that level of transparency that allows us to assert as discoverers and authors that we've done everything we can to root error out of that process. So here's the claim that computation really presents potential third and fourth branches of the scientific method until we have comparable standards to the first and second branch about what it is that's our version of the proof or our version of the level of transparency that allows us to verify and reproduce those claims that are actually being made that have a computational component somewhere. So I'm asserting we're not quite there yet. We have a little bit of work to do. Now, that's not a particularly strong criticism, I don't think. These first two branches have had hundreds of years to develop their standards around what comprises a sort of claim to the community and what the standards actually are. We've been thinking about this maybe 20 years. So, okay, next slide, please. Okay, so one of the sort of pithy quotes that I like and you often hear around reproducibility issues is trying to understand what the article or the sort of scholarly publication, what role that serves in a computational environment. And there's a notion called really reproducible research. This was developed, these concepts were developed by now emeritus professor John Claerbout, who is a professor of geophysics at Stanford, and he started noticing this gap in our dissemination of computational research in the late 80s and early 90s. And in 1992, he made these assertions around producing really reproducible research. He meant computational research by delivering all these facets that someone would need to independently verify the results. So data and code that produced the results, workflows, and so on. His approach was summarized by David Donahoe in 1998, where he's talking about the idea of really reproducible research is as follows. So an article about computational science in a scientific publication is not the scholarship itself. That's just the advertising of the scholarship. The actual scholarship is the complete set of instructions and data that generated the tables and the figures or whatever your findings or claims are in the publication itself. So that goes right back to nearly the first slide where I was talking about scientific findings, methodological innovations being embedded, for example, in the software, and the importance of having those innovations exposed to the community and the transparency of that entire pipeline to the discovery itself. Okay, so sometimes people ask me a question and they say, something along the lines of, well, who cares if you can run someone else's code or sort of visit all their computational steps on the data that they started from, like whatever the input data is, and carry out their same visualization techniques and sort of exactly run their code as delivered from them. That's not actually a scientific advancement. So I think that's exactly right. However, if you actually do contribute a scientific advancement, so that would mean, say, redoing the experiment or replicating the experiment independently, so I would go out, recollect the data, or regenerate the data de novo, and recode all the methodological steps that were necessary to get to that finding, and then hope to get the same finding as the original author. You're never going to get the exact same finding, right? Not down to like the 10th decimal point or whatever it is. You're always going to end up with probably a finding that's more than a few decimal points off from the original author. So I think what we need is really both. We need this level of exposure and transparency around the pipeline that's almost, or actually at the level of being able to run the same steps or visit the same computational procedures on the same data to get the same results, so that I can compare two different approaches to the same problem. If the results are different, we get different findings, then we're trying to answer the same question, I need to be able to do that comparison in the discovery pipelines to understand why they're different. So maybe one has done something in a better way than the other, or one has overlooked some really important part or step in the process and allowed error to creep in there, and I need to resolve which one is doing what. So we really need both, and it's true that if I just sort of run your code on your data and get your same computational output, I have an advanced science. However, it opens the door for us to be able to reconcile different results when different researchers answer the same question in different ways and get slightly different answers. Okay, next slide. Okay, so I've tried to build an argument around the importance of scientific verifiability for a deeper exposure of computational pipelines that underlie research findings, but there are many practical reasons to think about reproducibility is an important issue and potentially a frame for discussions in the research data community. So one is the concept of reproducibility. It provides a role in the discussion for not just data, but for software, code, for workflows, for other scholarly artifacts, digital scholarly artifacts that may underlie the claim that's being presented itself. So a discussion, say, for example, around open data is somewhat limiting in the sense that it doesn't go all the way to things like, well, what code did you use? Remember we were talking about outliers and how you prepared your data set? Well, all of those decisions are represented in code. So thinking about the lens of reproducibility helps bring all these other aspects of the research pipeline to the fore and part of the discussion, just like we have done with data. Another practical point to think about is when you talk to researchers about reproducibility, so in their own work, they have a pretty good idea of what it would take to make it reproducible. Sort of broad community-wide agreement on definitions and reproducibility is still under discussion, and they may differ by community and research area, but each scientist has a pretty good handle on what reproducibility means and what they would need to get out there, what information they would need to share to make their work fully reproducible. So that's a real win. When you talk to the research community and they understand what you mean, right? If you say something like, share your data or open data, it's not clear to researchers what that means. Like, is this all the data? Do I take the raw stuff off the instrument? Or what about different versions? And what do I actually share? If you frame pose the question more around, well, what would it take for people to reproduce that finding that you're asserting in the scholarly record, in your advertising of the scholarship? They're like, oh, I know what I need to do. I need to put this data set out there with these scripts and these input parameters, or whatever it is they actually did in their work. Okay, so the third point that I wanted to make is that I think there's an opportunity here. We are seeing now, I think, the convergence of two trends that are going to help us in this discussion. So these trends, you might think, actually are at loggerheads with each other. So the first one is that we're seeing research projects become massively more computational. So someone mentioned to me the other day that a typical PhD in a computational field would probably take about 1 million CPU hours. And this is something that I don't see this slowing down. So this is something that's continuing to increase. Now, this is also paired with discussions like the one today and many other discussions that are happening and research that's going on to ensure the transparency of scientific computing. So anytime you have a computational aspect in your research pipeline, we're moving towards greater transparency in the computing and in the pipeline, exposure of the pipeline itself. So these may seem like they're fighting. We're becoming more computationally intensive, and yet our demands on how we're doing that computation are increasing. Next slide, please. Okay, so the argument is I don't think they're actually antagonistic. I think these trends are actually converging and supporting each other. And the reason that I think that is because when you are running these and carrying out these much more computationally intensive projects, they get more difficult to manage and run. You're running a lot more jobs on a lot more data, using a lot more resources, computational resources and so on. You're going to require a greater level of transparency just to keep track of your own jobs and your own research. And what's happening now is that computational infrastructure itself that's just necessary to run these bigger experiments is going to bring a level of transparency and organization just naturally as we develop the technology. So next slide, please. Okay, so what this makes me think about is efforts, some of which that I think are underway already today, but to develop this infrastructure that will promote good scientific practice, things that, I've never heard a researcher say that transparency and reproducibility aren't good, desirable things, so that move us in that direction. But people aren't going to do it, I don't think, because of the first part of my talk, sort of this hopefully interesting philosophical discussion about the importance of reproducibility and the framing. What they're going to do it for is because they have to manage a massive amount of computational work. So efficiency, productivity, acceleration of discovery, this is why computational scientists are going to end up with a more transparent record and a more easily shareable and reproducible set of scholarly artifacts coming from their research. So next slide, please. Okay, so I promised that I would get to a sort of little bit of a vision about where I think maybe the scholarly record could go as we start to move towards greater transparency in our computational infrastructure that underlies discoveries and sharing of more transparent pipelines when we make those discoveries available to the community. So I borrowed these sort of 5 queries from Donahoe and Gavish they were published in 2012, and I think they represent queries that are very natural for a researcher in these areas to want to make. So queries upon the scholarly record. And I'm just going to kind of read them out to you because I think, like I said, they're very natural, yet very difficult to actually visit on the scholarly record as it is today. So what I want to do is sort of prompt thinking about how we actually make these objects discoverable, searchable, and available and persistent over time. Okay, so the first one is I might like to query the scholarly record to return a table of effect sizes and p-values associated with all the phase 3 clinical trials for melanoma that were published in 1994. So just give me the sort of significance of the finding associated with its p-value, and just give me a table. I would like to make a query on the scholarly record that returns all the image denoising algorithms that have ever been used to remove white noise from the famous and widely used Barbara image, and return a list, sort of labels of all these algorithms with their citations of where they were actually used in the scholarly record. This would be a very natural query for an image processing scholar who might like to start building on some of these algorithms and develop new algorithms to know what actually has been used out there. Also a very challenging query. I would like to have a list of all the classifiers, the machine learning classifiers that have been used on the famous acute lymphoblastic leukemia data set and give me their misclassification rates. So return that table so I can actually compare what was done and which algorithm might be working better than others. Return to me a unified data set containing all published whole genome sequences identified with the BRCA1 mutation. So really hard. You could even ask a query on the scholarly record to do creative things like randomly reassign treatment and control labels to cases in a particular published clinical trial, and then recalculate the effect size. You can do this, repeat this many times, and then come up with a histogram for all those repetitions of effect size. So I could choose a year, say 2003, and do this randomization, sort of bootstrapping, for all the clinical trials published in that year, and I could show that histogram with the clinical trial label side by side, so we could really get in a sense for what effects are actually happening in these clinical trials. Next slide, please. So we actually, with a student, I did a deep dive into query 3, the one about returning the machine learning classifiers that had been applied to a very famous cancer data set. So this cancer data set was published with an initial classifier in 1999 by Golub et al. And what they are trying to use is use genetic information to assess whether you have acute myeloid leukemia or acute lymphoblastic leukemia. So they're just deciding between the two in this data set, which I did with 2 students, Xiaomian and April. Next slide, please. So what we wanted to do, we were just going after the query. We wanted a list of all the classifiers that had been applied to this data set, and I wanted to compare their misclassification rates. So when we did the literature search, we found 30 articles. So that's not even an easy search to do it by who used this particular data set. And then what we did is we tried to create this table of misclassification rates. So we did a deep dive into 5 articles where this seemed like we might be able to do it. Next slide, please. So for our 5 articles, what we found was a lot of differences, not just in the algorithm, the machine learning algorithm that was applied for the classification, but deep differences in how they did their data pre-processing, how they did their feature selection in preparation for the application of the algorithm itself. Next slide. Okay, so this didn't come out as strongly as what I would like, but what is going on in this slide is I'm trying to show you pictographically how each of the 5 articles, how their research pipeline is very different. So, oh, by the way, I should mention, my slides are on my website, so if you wanted to just sort of follow along on your own device or whatnot, or look at the actual color version of this slide, feel free. So they're all just sitting there on my website. So what's happening here is I'm trying to display in sort of flow chart form the decisions that were made as researchers went through this pipeline. So there's very deep differences in the pre-processing, in the validation steps, in cross-validation, for example, where this was visited in the research pipeline, in feature selection, extremely different feature selection decisions, and then how the actual model was applied and tuned and so on. So hopefully you can see that at least these 5 clusters of blobs are really different. So the pipelines are so different, making them really difficult to compare the output. Okay, next slide, please. Okay, so this took us over 200 student hours to even get to this point, and not all of these papers started from the same version of the Golub data set. The pre-processing steps were different. Feature selection methods were very different. The algorithm they chose to do the classification was very different. How they tuned their algorithm was different. And what they did for model validation steps were really different in how they made those decisions. And all of these details were not well captured in the paper. So that's why we kind of reduced to 5. Those 5 were kind of the most clear and transparent to us. So our job to compare those misclassification rates in the different studies would be easier if they all started on the same data set, if they had prior agreement on their test data, so their holdout data, if they weren't kind of splitting the data set all different ways to do the tests. There was full disclosure of all their pre-processing feature selection steps that went into the application of the machine learning algorithm, and then a full disclosure of how they applied the algorithm, how they tuned the parameters, and how they set up their model. Next slide. Okay, so I think infrastructure comes to play as a unifying force for how we actually carry out and compare different results and compare different pipelines. So there's a notion of the common task framework that comes from natural language processing and actually comes from machine translation, harking back to discussions that they had in that community in the 60s. And what they did is they decided to agree on data sets prior to analysis, and then they held conferences around those particular data sets. Holdout data was held by a neutral third party, so the researchers never saw the holdout, the test data. Actually, the third party is NIST. And then researchers, what they would do is distinguish and specify feature selection, pre-processing steps versus the model selection and the machine learning application steps. And they would send their code off to the third party, and the code would then be run on the holdout data, and the results, your misclassification rates, sent back. So what that structure allows is you can actually directly compare the pipelines, like the different steps that the different researchers took, and you can directly compare the misclassification rates so you have some sense of which model works better. Okay, so I think infrastructure that supports computational experiments can facilitate this comparison of the results. So now we've got an apples-to-apples comparison, and more deeply it can start to facilitate understanding why those pipelines are different, as well as corollary effects like reuse. So I could take out a machine learning algorithm, slot in another one, and this sort of modularization that allows us to repurpose a lot of the work. Next slide. Okay, so a very brief history that I'll just step through quickly of computational reproducibility, our third element of reproducibility. Next slide. So starting in 2009 and building on the ideas that Claerbout started promoting in the very early 1990s, there was a declaration that came out of a roundtable held at Yale around access to data, access to code, and sharing of these artifacts. This was followed on in 2012 with an ICERM workshop at Brown. Essentially, the workshop report that came out of that gathering tried to assert that the default should be the availability and openness of computational artifacts that underlie a particular scientific claim, rather than the exception, which we were seeing at the time and still seeing now, where sort of researchers sort of step up and maybe voluntarily make these things available. There was also a workshop prepended to the XSEED annual meeting in 2014. It's a little hard to read there, but it says reproducibility at XSEED. So thinking about how can existing infrastructure actually provide support for reproducibility. So XSEED is an interesting discussion because of the way it's structured. It actually acts almost kind of like middleware in between computational resources and the researcher itself. So maybe it's ideally positioned to capture some of these computational details as they're being visited upon, the computational resources. Other aspects like gateways and so on could start to maybe think about, or they do think about that aspect or that potential role that they might have in supporting research. So these are some of the steps that have been taken, and it's obviously not sort of a very brief history, and it's not a complete history. If we could go to the next slide. So this is the workshop report from ICERM, so setting the default to reproducible or setting the default to open. We had a couple of publications in SciAm News and AMS, American Mathematical Society. Next slide, please. And I'll just go quickly over this, but of course we don't see just efforts coming from the research community to grassroots level. We also have seen the 2013 Open Data, Open Access Executive Memorandum and Executive Order. So also sort of governmental or regulatory nudges, or sometimes more than nudges, around access to data or access to scholarly artifacts. And this has resulted in many agencies and other government entities, including NSF, for example, really taking huge strides towards public access to research artifacts that are created in the course of their grants. So next slide, please. Okay, so just some snapshots of some of the steps that NSF has taken in terms of directorate-wide discussions around reproducibility and rigor and reliability. Steps NIH is taking, they have a website dedicated to reproducibility and detailing steps that they're taking in their community as a funding agency to enable greater reproducibility. Next slide. I'll mention in February, so this is an NSF workshop on Systematic approaches to robustness, reliability, and reproducibility and in scientific research. So this came from the MPS Directorate at NSF and brought together community members to assess where they stood for research funded in parts of that directorate in terms of reproducibility and needs and so on. And it really highlights the importance of community-wide discussions and the fact that none of these steps, even if there's broad agreement, get taken without discussions and people being on board and shaping the nature of that conversation and the steps forward. So next slide. I'll mention also in April, so this is National Academy's report that came out called Fostering Integrity in Research. And I wanted to highlight, since this just came out in April, 2 recommendations that go to reproducibility. So recommendation 6 and 7. So recommendation 6 says, so notice it says, through the development of supporting infrastructure, all sorts of research sponsors and journals, publishers should ensure that information sufficient for a person knowledgeable in the field and its techniques is available to reproduce reported results at the time of publication or as soon as possible afterwards. Recommendation 7 suggests that funders, writ large, should think about enabling long-term storage, archiving, access to data sets and code necessary for replication of published findings. So next slide. So this is an article that came out just in December of last year, Enhancing Reproducibility in Computational Methods. So what was happening sort of in the subtext of this article, I was one of the authors. This came out of a series of workshops funded by the Arnold Foundation. And here, one of the things that we wanted to do was really, sort of going back to where I started in the conversation, elevating things like code and workflows and software in the discussion to the level of, say, data in the larger policy discussion. So next slide, please. So we had 7 recommendations that I'll just mention very quickly. Facilitating reproducibility, so getting data, software, workflows, details of the computational environment out there with the publication. And providing links in the publication was recommendation 2. So it doesn't make a lot of sense to kind of read a paper and then start Googling around for, well, where's the data or where are the workflows that go with these results, so making that kind of seamless. Recommendation 3 was start citing. So citing code, data. If you publish, make your code or data available that you use in those, the results in that paper, cite yourself and sort of help the community start to develop sort of citation norms for code and data the same as we do for publications and ideas. Documentation was recommendation 4, sort of a larger discussion. Journals could actually play a role in checking reproducibility as well as existence of artifacts. Recommendation 6, very important that these objects are licensed so that you are enabling reuse, so using open licensing to enable people to download, copy, cite, for example, modify, reapply code, data, and so on. Our last recommendation was to recognize that these are not solved problems and there is a research agenda here and how different communities can go towards enabling these facets of reproducibility. So next slide. Okay, I think I'll skip this in the interest of time, but what was happening on that slide is that journals are also taking steps around requirements for code and data exposure. So this slide, what it does is it says that there are many different, these are often grassroots efforts around creating infrastructure to deliver a pipeline that captures the important parts or what the researcher and the developers think are important parts of the research pipeline to make greater transparency in the publication and sharing of the work. So it roughly kind of divides in innovations in research environments, in workflow systems, in dissemination platforms. One thing that I think is really fascinating is many of these projects are done by academic researchers without sort of formal recognition or incentives to do this, so they sort of do it on their own time, and they just think it's really important. So there's a few commercial up here, but most of them are actually just from the research community. So next slide. Okay, so this is my last slide, my concluding slide. So I wanted to leave you with 3 thoughts around the role of infrastructure, which, as I've been trying to make the case throughout the discussion, is I believe will be instrumental to how just about all scientific research is carried out now and going forward. The first one is the infrastructure. There are always design choices, and supporting scientific norms, going back to Merton, going back to Boyle, is extremely important in the infrastructure itself. And this is a special set of norms that go towards science as different to how we might use other aspects of computational infrastructure. We want to support best practices of scientific research in the architecture and the infrastructure itself. So I mentioned earlier in the talk statistical reproducibility. So if you are doing something like visiting all sorts of statistical tests on your data and then cherry picking results and publishing those particular ones, that's called p-hacking. Infrastructure can help track the tests that were done and report results with the full context, for example. So it's possible to think about infrastructure design for research discovery that actually enables best practices for the discovery itself. The last one is taking the holistic approach to cyber infrastructure, thinking about the end-to-end pipeline, thinking about things like the data generation mechanisms or collection mechanisms and experimental design at the beginning of the project, right through to conclusions or testing right at the end and everything in between. So what were all those steps, and can we capture that? The computational aspects as part of our cyber infrastructure design. It also goes to issues around sort of integration of the scholarly record, so we don't end up in a situation where artifacts are sort of very distributed and not well linked, or sort of links become an issue around how we actually pull together claims in the PDF and the publication with the underlying data, with the underlying methods, code, software, and so on. So we really need a more integrated, sort of holistic approach, and CI can help bring that around. Okay, so I will stop there, and thank you so much for your attention this morning.
So acknowledging that we are going to eat slightly into our coffee break, I would like to take just a moment if anyone has 1 or 2 questions for Victoria.
So I would suggest going to a mic if you have questions, or, okay, great.
Thank you very much for your talk. Jim Wogenbush, University of Minnesota. I wonder if you have any thoughts about the sort of increasing data that's collected in the private sector, as sort of, especially in ag research, the focus has shifted greatly into the private sector. When you bring sort of the paradigm of open data, that tends to make a lot of the people that you would work with in that sector run the other way. So in fact, instead of getting more cooperation and potentially collaboration in the big data space, you could potentially get the opposite. I wonder if you might be able to comment on that.
Yeah, so I do have thoughts on that. So the first one is, it's a dynamic problem, right, and an ongoing discussion. So there are many caveats around open data and open code. I just would have loved to have gone into in my talk, just in the interest of time I didn't dig into. So one of them, for example, not all data is shareable. So you may have data with privacy concerns around human subjects. Of course you legally cannot just sort of dump that in an open repository, for example. And I do think there are sensitive issues in the collaborations with industry that need to be navigated. I take the view that industry, like I said, it's dynamic and it's an ongoing conversation, but sort of at a 30,000-foot level, that there is a socialization aspect. So I have seen in the academic research community, since I've been working on this issue, when I first started giving talks on this issue, I actually got, people standing at the back of the room and sort of, on some of the things I was saying. And I have seen those very same people who are leaders, academic leaders in their community and so on, at some point they flipped. And they now are great supporters, and they sort of act like they've always been great supporters of the things that I've been saying, and so on, which is fine with me. I know exactly who they are, and I'm not going to say anything. But I think the same thing can happen at the industry level, too. So they obviously have real issues around protecting proprietary interests in the data and so on. However, many of the engagements that we have had with academic companies have sort of had even sort of NDAs associated with data, and it's kind of this complete lockdown. And I think that there is an opportunity for negotiation there to say, okay, maybe there are ways to expose parts of this, and maybe there are ways to expose it in similar ways that we might expose confidential human subjects data, for example, through gateways or authentication or whatever mechanisms we're also developing for those types of data, and sort of gently kind of move that conversation forward. I think it's almost a kind of a reflex from some companies to sort of say, well, you know, just keep as much locked down as possible. I mean, we're in a competitive environment. And I think the sort of the needs of scientific verification and the acceleration of discovery that comes from that kind of increased transparency will help that conversation forward. So they might not end up in a place where ideally we as academic researchers and in the academic community might like to see because of sort of real limits on what they can do. On the other hand, you have the situation where results are being published in conferences and in journal on data sets that are complicated and we have no ability to verify using computational stacks that come from that particular company that we have no chance of verifying, and we're supposed to just kind of believe these results that are coming out, which isn't a satisfactory situation either. So I think I'm very optimistic that that's a conversation that will evolve if we, I agree with you that the right thing is not to just march up to them and say, okay, everything's got to be open from now on. Right, I think there is this ongoing engagement that we can be sensitive to, but I don't think we've exhausted the limits of potential openness on their side yet. And I think in university tech transfer offices can help play a role in that discussion and thinking about how we actually engage and what contracts we're using with them and what do we actually accept from their side is this larger ongoing conversation that's very important. Yeah.
So I'm Jaime Comariza from Johns Hopkins. So a few communities, or I better say a few members of some communities are now doing a practice to publish what is called executable papers.
It's called
executable
what?
papers.
Yeah, right.
So in addition to the publication, they provide access to the scripts, the pipeline, and even the data. So these people believe in sharing data, in validation, and so forth. So whoever wants to do that, they can easily do that.
Yep.
This is not a standard. Only a few people are doing that. So, and that's what you describe in your talk. So what should be done for this to become a standard, and with the same as with data management, to enforce that?
Yeah, that's a really great question. So I think, the first thing is, I think it's very difficult for anyone to sort of stand up here and say, this is how you researcher, data manager, and so on must do it. So here's the path forward. And I think that because there are a lot of different pressures on both researchers and infrastructure providers. So to be specific, so some research, for example, is extremely computationally intensive or code heavy, and they have a particular notion of what it means to share their work, and they have XML files of their input variables and so on. On the other hand, you have researchers who maybe haven't done as much computation, but their work is in the data collection, for example. So you sort of see these sort of very different and culturally very different places where different research communities are in terms of accepting these ideas. And so, and where they go might be different. So the executable paper might be one place that communities will end up, but you might see different communities ending up in a different place because they just happen to work on such large data sets that a self-contained executable paper isn't necessarily the right solution for them. However, one of the things I wanted to do in the second half of my talk was really show that this is a collective action problem. So journal standards play a part, funding agency requirements play a part, institutions play a part in terms of what resources and support they can provide and what it looks like, and also what does it take to get a job there, what's involved in promotion and tenure. If the metric is PDF publications, it's very difficult to get buy-in, particularly from junior folks, around making a full executable paper, for example. But how things look and how the solution actually looks, I think, is changing from the underlying changing technology. It's such a rapidly changing space, and we have all sorts of innovations happening to better deliver transparency and reproducibility, but also just sort of these cultural needs and what's acceptable to the community. And that sounds like a bit of a waffly answer. However, I have seen things move so quickly, even in the last 1 year, 18 months, that I'm still optimistic that this is a discussion that's extremely progressive and will result in the right solutions for the right research problems. So in terms of standards, things like this discussion today are incredibly important, and having facilitated meetings, for example, in dedicated research communities to sort of engage across silos for different research areas where they may not even sort of hear of, like, biologists may not hear about a great solution to one of their problems that's happening in the geosciences, for example. So sort of trying to have that sort of cross-disciplinary discussion, which is not how our community is designed, can also help kind of bring around an agreement and convergence on these standards. Okay.
Would everyone join me again in thanking Victoria? Could we please have our panel one members up onto the stage? All right, so our first panel today is on campus support and challenges related to RDMI. We are grateful for the assistance of our moderator today, Rajendra Bose, who is the Director of Research Computing at the Mortimer Zuckerman Mind-Brain Behavior Institute at Columbia University. He is the 2017 Chair of the Coalition for Academic Scientific Computation, CASC, and a 28-year-old organization dedicated to advocating for the use of the most advanced computing technology. Take it away.
Thank you, Wendy. I'm very happy to help with moderating this panel. I think that the organizing committee has done an excellent job in very carefully forming a panel which are going to give a mix of perspectives, both from a research point of view, those of us who help with infrastructure on our campuses, planning from a college level, and preservation perhaps from the libraries and other topics. So in the interest, I'm going to channel Wendy, and I will try and stay as close as possible to our 60 minutes allotted time. We may cut into the break, but I want to give people a chance to speak. What I'm going to do is I'm going to go in the order that the speakers are listed. I will just introduce them as they come up to the podium. I'm going to hold them to a 7-8 minute time limit. I'm going to actually sit in the front row and I'll give a hand signal. And we'll just, and then there should be time for questions at the end. So we will try and stay close to time. So the speakers basically have been asked to address a few things, including challenges for data management on their campuses, institutional support through the entire life cycle, and also the primary drivers for research data management. So we'll be hearing from our 4 speakers. So the first speaker is Juan de Pablo. He is from the University of Chicago, the Liu Family Professor of Molecular Theory and Simulations in the Institute for Molecular Engineering and the college, and he is a senior fellow in the Computation Institute. So please welcome.
So thank you for the opportunity to address you this afternoon, or this morning actually. So just building on what was said by the previous speaker, there's a tremendous interest in reproducibility, making data available, etc. These are articles that appeared in prominent journals in just the last 2 years. And the key point is that more and more of us would like to make our data searchable, identifiable, and store it for the long term, right? Two of these papers came from science. Science seems to be having a crisis with reproducibility. And in this article by Schrag and Purdy, they mentioned that the standards for science should actually be higher. And that's something that would be interesting to consider. Should the standards be different for different journals and different disciplines and different institutions? Now, from my perspective, some of the primary drivers for research data management are, first of all, the fact that scientific progress and scholarly pursuits are built on the work of others. Me, as a theoretician, I do not know whether I understand the theory or a problem until I can reproduce every step of a calculation, for example. And I'd like to accelerate that process. So we need an infrastructure, really, that allows us to exchange data and code and results more efficiently. Now, secondly, we have to realize that as academic researchers, our groups, our research efforts are always in a state of flux. Students come, graduate, and every time that we have a student or a postdoc leave, all of that knowledge is lost, and we have to start from scratch again. So we'd like to be able to put measures in place that allow us to actually pick up exactly where we left it. When a new student comes in, everything that was done by the previous students was documented. You know exactly where to find it, you know where to find the data, and you can reproduce everything that was done. Now, our previous speakers said that computational science has become a recognized third branch of science, and I was giggling a little bit. Giggling because I'm old enough to have been a part of those discussions 20 years ago, trying to defend computational science. Giggling because you'd be hard-pressed to find any student under 25 who's an engineer or a scientist who doesn't view computational science as an integral part of everything that they do. So I think we need to move beyond that and really put the infrastructure in place that allows us to use and exploit computational science to its full extent. Finally, open science. I think there's increasing pressure from funding agencies and the public to make all of our data available, and I share those pressures. So we need to come up with mechanisms that allow us to publicize these data. So what do we need then to meet these challenges for the scientific community? So first of all, we need to build an academic culture that accepts and supports these RDM workflows and practices that enable reproducible science. This is easier said than done. For example, I'm a computational scientist or a theoretician. Many of us believe that we should make our codes completely available to the public. Now, these are codes that took 10, 15, 20 years to develop. Many in my community think that this is actually the product of their work. Those codes are worth money, and they don't want to make them shareable. So how do we deal with that problem? So we need an academic culture that actually accepts and supports these transfers of data. And secondly, if we're going to make these codes available and this data available, we need to develop the tools, the infrastructure, the software that allow us to do that in a seamless manner. If I ask a student to make all of these codes and all of these results available, this has to cost no effort for them. It has to be trivial to store that in a place where it's safe and curated and searchable. So our institution, the University of Chicago, has been very proactive in developing an ecosystem that allows us to do just that. One that I've been involved with is actually shown over here. This was a work that was supported by NSF. This is a DMREF project. And all of the infrastructure you see here was developed by Birali, who's our workshop organizer, and his staff, according to our demands and our needs. And I think it is a very interesting first step in the direction of what I was trying to tell you. So if you could actually click on this website for a moment. Whomever is, hello? All right. So that's the website where we store our data. Can you type my name over here, De Pablo, D-E space P-A-B-L-O? Space. All right, search. All right, so all of the papers that resulted from this project are actually loaded here, all right? What you'll find in this website are all of the figures and tables that were part of the paper, the PDF of the paper, of course. You can download all the data, and here you have the workflows, a notebook that tells you exactly how all of these figures were generated. So why don't we go to figures and tables here. All right, so you see now all of the figures that were in this paper. And what's important here is not the fact that we have the figures here, but that we have all of the tools that you need to work on the data, calculate anything that you want to calculate on those figures, and reproduce exactly the figures that you see over here. And what is remarkable about this environment is that it's really painless. You follow a set of instructions on the web where you put in your codes, you put in your data, you put in your figures, and everything can be regenerated. Wouldn't it be nice if at every single university we have something like this in place to do our research? Then the problem of managing your research group would be eliminated or minimized to a great extent, and we'd really be able to be much more efficient in the way we pursue our work. So I think with that I'll stop. No, I'm done. And I'll be happy to leave the podium to our next speaker. Thank you.
Thank you very much. In the interest of time, I'm going to introduce the speakers and we'll have questions at the end. So our next speaker is Preston Smith. Preston is the Director of Research Services and Support at Purdue, and he oversees the delivery of Purdue's Community Cluster HPC program.
All right. Well, so I've got only about 3 billion slides. I could probably talk for about half an hour on this, but I'll be respectful of everybody's time. So if we can go ahead and advance. Oh, do I have a clicker? Oh, I'll be darned. Great. Okay. So as a research computing provider, I'm just going to touch real briefly. We have a site at Purdue, PER, which is built on the Hub Zero platform, which does the data curation, data management plans, and all the things for the long-term preservation. You know, this is another topic that would be great to hear about, but since we've already got some library representation here on the panel, I'll just move past this. But just be aware, we do have something in that landscape. So the first building block in our research data management infrastructure is our community cluster program. One of the early institutions where we did condo-style computing. We build one of these systems every year where faculty members can pool their money and get a much larger system than they can build on their own. Since 2008, we've built 9 different HPC systems, every one on the order of 500, 550 nodes. And we're in the process of building our 2017 system here back on campus right now. So the simulation and modeling aspect of data management, this is historically at Purdue, been where we've been far ahead of the actual data. Our partners are represented from all over campus. Being a strong engineering institution, we're heavily represented in the physical sciences and engineering. But if you look down towards the bottom of the list, we've heard this refrain a couple times already this morning, is that people are coming with data needs and computational needs from all sorts of new disciplines. There's entomology, botany, all sorts of humanities or agriculture. So for data storage, as a campus resource provider, we provide really three different tiers of storage. All of our cluster systems have large parallel scratch file systems. We have a lab project storage named the Research Data Depot, where our researchers can come and purchase storage and work on their data actively. And we provide a tape archive built on HPSS for all researchers that use our other resources. There's about 9 petabytes in that right now. And then PER figures into this larger ecosystem as well. So I always like to keep this chart up to date. We're all, I think, all too aware as to the growth rate of data on our campuses. So every month I generate the new plot of this. Our Fortress archive is shooting steadily upward, near 10 petabytes of usable data. We ran this archive since the mid-90s, and it took 14 years to reach the first petabyte in the archive, 14 months for the second, 9 months for the third, and it's just going up. So I think it goes without saying that this is certainly one of our research data management challenges. How do we make this a sustainable resource to provide to campus? Because it's clear to me that people need this. Between Scratch and Archive, we've heard many different requests from our researchers, which I won't read through here, but if you skim those, those of you that run campus centers, a lot of these may sound really familiar to you. So in 2014, we had 20% of our requests that come into our HPC center involved working with data. So we came up with our Research Data Depot system in 2014, and this is a storage as a service, kind of condo-style storage. So $75 a terabyte, we can provide this reliable, high-performant storage to any researcher on campus. We've had over 400 research labs that have invested money into this. Many of them, 60% in fact, are not HPC users. These are not people who use our clusters. They just need a place to store data, work with it, and share it with their collaborators. The average research group has purchased nearly 10 terabytes of storage. So we have some tools to set up some storage patterns to encourage some good data lifecycle. They can create directories for their students, put their data in one place, applications in another, organize it by projects with access control, whatever they want to do. The faculty members are given a self-service tool where they can manage their own access, so they don't have to go to IT to file tickets and get people added to groups. They can do that themselves. Globus is a key part of this ecosystem. Like I mentioned, they have data, they want to share it and transfer it with people, and we've seen tremendous growth in people wanting to use Globus. In the last 12 months, we've moved almost 2.5 petabytes. 1 month in March was 388 terabytes, and my first guess when I saw that, like, oh, that's the climate modelers sticking all their data in my HPSS system. It turned out it was not. It was a grad student from industrial engineering who I never would have thought as one of our traditional big data people uploading something into one cluster. So it's a great example as to the fact that everybody needs this much data. And then Globus has helped the archive. 1 3/4 petabytes moved into the archive with Globus. So the first challenge is working in a condo-style storage. The faculty members have to pay money to use the storage system. So some of them have already given us feedback that if I need to buy 200 terabytes of data storage, that's a fairly substantial piece of my grant. So how can they make that sustainable and affordable? Their position is that the administration should pay for that out of their overhead. The administration may have a different opinion, but at some point that's going to have to be resolved. So this is one of our data sheets as to who uses our systems from around campus. This is a number of PIs from these academic colleges. So this is somebody that uses either our HPC systems or our data storage systems, so they're paying us for some sort of a research computing service. But I always look at the growth in agriculture. So we had 48 PIs in 2014 and 111 in 2017, 131% growth. But what's really interesting about that is that out of that 111 PIs, only 30 of them are HPC users. So I'd always talk about our agriculture researchers as being pre-computing. At some point, they're going to need high-performance computing, and then they're going to have to find something that's appropriate to them, which is our second challenge. There's gaps between solutions that we have for some of these resources, for some of these communities, and what they have to work on it. They might be working on their laptop right now, but they want to run bigger problems or longer problems or more complicated problems. But batch HPC is probably not the thing for them, so how can we do that? So we're deploying a system right now called the Data Workbench. It's for interactive computing. We've had a lot of these technologies on campus, but not wrapped up in a package and tied in a bow. We'll provide remote computational desktops for people to run MATLAB, RStudio, all those things that they do on their laptops, use Jupyter Hub notebooks, use RStudio Server, make those tools more accessible to them without having to navigate a high-performance computing cluster. A low annual cost, and give them the ability to run Windows VMs, run Linux containers, integrate with all of our HPC services, and most importantly, use that as a lever to get them started in computing. Eventually, they'll outgrow it and need to go into the batch world. Our third challenge, secure data, is more and more important. We get a lot of funding from defense and things requiring 800-171. We don't have a medical school, so HIPAA we've dodged so far, but that won't be for long. And then challenges 4 through 9. I know we were only asked for 3, but I figure that's there's no way I can hold to that. But just real briefly, networks is a challenge for researchers. If you need to transfer and move data, We've got to get it over the network. We have a science DMZ, but the rest of campus likes to militarize their networks. The core facilities with instruments have data management problems and data storage problems. People are starting to talk about streaming data, databases, object stores. We don't have that. How do we get from the HPC systems into PER? What's our cloud strategy? Purdue is one of the only institutions that somehow has not gotten a Box.com or a Dropbox contract that I know many of you have, so we're going to have to figure that out. And then data sets. How can we make those available for researchers who need to use those on computation and manage their access? Okay.
Great, thank you, Preston. So we've heard so far from the research point of view, from service provider, and our next speaker is from the leadership angle. So let me briefly introduce Rachel Vincent Finley. She's on the faculty of Southern University and A&M College. She is an associate professor in mathematics and serves as associate dean for academic affairs in the College of Sciences and Engineering.
Good morning. Okay, I have slides. Thank you for the opportunity to participate in this discussion. So I wear two hats. I am a researcher and now a newly knighted administrator. So I get to see, I get to complain to myself, essentially. So I just want to go through quickly what's going on in the state of Louisiana. So given all the hurricanes that came through, we could appreciate that we need to do a lot of work in the use of our infrastructure and storage. So just a bit about the Southern University system. Southern University is an historically black college and university. It's an 1890 land-grant institution and currently has campuses across Louisiana, Shreveport, Baton Rouge, and New Orleans, and the lead campus is our Baton Rouge campus. So given that we're in hurricane-prone areas, we needed to think about infrastructure, particularly post-Katrina. We had essentially a loss of a lot of data, a lot of resources, and a great brain drain when individuals had to leave New Orleans due to the flooding. Excuse me. So I wanted to address quickly some of the key points that were asked of this panel: greatest challenges related to data management, institutional support, and primary drivers that I see for research data management from the perspective of my home institution. So I just list them all because if I did smaller bullets, I might be up here for a long time. But essentially, there is a problem. Some greatest challenges I note from our particular perspective are data formatting issues, data storage issues, and resource limitation. So we're dealing with these issues, but they are recurring issues. We have several several research centers housed in Louisiana and a new research center housed at Southern University in Baton Rouge in partnership with Louisiana State University. And we have a collaboration of researchers across disciplines. We have chemists, we have mechanical engineers, we have physicists, we have mathematicians. So we have different types of data. We have wet labs, experimental data. We have the computational scientists, our computational data. And then we have that we have to collaborate and support this data through publication and think about how each of these different disciplines need to use this data and how we can, the big question of the reproducibility, because now this data is coming from various sources. Everyone has their own way of storing the data. How do we come to some kind of collaboration and a unified way in which we could, number one, support our research, and number two, provide good information back to our funding agencies. So the data storage information, how do we do this? Where do we store it? How long do we store it? Who has access to this information? And in those instances where we may be using sensitive data, human data, how can we provide good information without compromising private data? And then we have different issues for data retrieval and dissemination. So we'll talk about some of these things and if we have time a little later. So one item that I note for so far as institutional support is after Katrina, Hurricane Katrina hit New Orleans, the governor at that time of the state decided that we needed an infrastructure so that if such things happen again, we have redundancy in our computational system and an infrastructure where our scientists could still work though they may have been displaced from their home institutions. So this is just a map of the infrastructure that was built out post-Katrina, where, again, this is actually one of the older maps. We have more redundancy in the system at this time. But the idea was and is to keep the knowledge and research going, even though we're in weather damaging area. I don't know how else to say it, it's just not good. So we want to have a way in which our researchers can stay engaged even though they've been displaced from their home institutions. And this is just a listing of our partners. We have, excuse me, let's go back one. We have partners in higher education and also partners with institutions within Louisiana Public Broadcasting, for example, and our Department of Transportation, all users of the infrastructure, and particularly Louisiana Public Broadcasting and the Department of Transportation, in that they provide information to help get our citizens out of the state or into safer areas post weather trauma, and Louisiana Public Broadcasting, because again, they're providing information not only in weather situations, but also to educate educate in our secondary schools. Ooh, I think I have cut this off. Okay, so I'll keep talking. I'm not quite sure what happened. Okay, there it is. So just to close out, primary drivers for what we see as things that we need to work on to get us through to the next level is collaboration. We need, in our research centers, we have institutional and statewide collaboration. We have the infrastructure to do the work. However, we still have a lack of support in the area of storage. There's short-term storage, but we need longer-term storage to support what's happening with to support what we're saying we are supposed to be doing with our research funding, and again, issues of data retrieval and dissemination. When we're storing these data, who has access to this data, how much of it can be public, and how do we clean data so that it all can be public. And again, evaluation of data, we have this research data, we have to have external evaluations, so we need to have research-supported ways in which to allow usage of this data, reuse of the data, and again, external evaluation is important in this whole process. I'll close out by noting my connection into various areas in my state. I am the Secretary-Treasurer of the Louisiana Optical Network Initiative. This is a management council that manages the infrastructure. I'm also an Exceed Campus Champion, and that's how some of the training happens within our state. Between Lonnie and Exceed, we do training to get people up to speed as to how to use the resources, and then thinking about the concept of, now that you're doing this computation, how then do you store the data for reuse? And I include my email address, and I look forward to questions concerning how we can better serve our communities. Thank you.
Great, thank you very much. So our fourth panel member, thank you for your patience, is Christy Ann Wiley. She's the Engineering and Physical Sciences Research Data Services Librarian at the Granger Engineering Library at the University of Illinois at Urbana-Champaign.
See that? Okay, great. Thank you. Good morning for the opportunity to be here today. Let's go with this. All right. The University of Illinois Research Data Service is supported and funded by the Office of Vice Chancellor of Research. This consists of a Research Data Services Director, Dr. Heidi Imker, who was hired in 2014, two research data curators that were hired in 2015. It also includes a partnership collaborative of institutional support from the University Library, the Provost Office, Campus IT, the National Center for Supercomputing Applications, as well as staff within the library, outside of the library, all working together in order to support the growing needs of faculty and graduate students. As far as infrastructure support, the University of Illinois has an institutional repository called Ideals that launched in 2007. As of 2016, we have the Illinois Data Bank, which has to date about 50 data sets and about 8,000 downloads. When we start a lot of our conversations on campus with faculty or research groups and graduate students, we definitely start with funding agency mandates and national data policies. In 2015, I conducted a study with the interim dean now, Bill Michaud, where I interviewed 21 engineering and atmospheric scientists as it related to their current research, and the funding that they were using at the time was NSF grants. This particular slide on the left hand side is where I continued that study in talking with bioengineers, chemists, life scientists, and bioengineering faculty. Some of them were talking about studying proteins. They were talking about brain cancer, advancing imaging technologies for eyes, eye and skin. And all of it was related to NIH grants that were greater than $250,000. On the right-hand side, that's the different types of formats. When I look at both of the studies, you can assess that while it's true that the size of the data and the format of the data varied, what remains the same from the library's perspective, that is that the majority of the researchers were aware that the university library provides support for data management and preservation services, yet few of them had actually used it. They were not aware that the campus had an institutional repository, and at least half of the participants in both sets of the studies said that they would be interested in having someone from the research data staff or the library provide instruction on best management practices for managing their data to their research groups. As far as what we've been doing, one of the initial things that we always do is we provide data management consultations on the data management plans. Another thing that we do is that we provide data management instruction that is targeted for specific research groups. And one way that we do that is we do what we call a data management engagement worksheet, in which we find out or do a research profile on the faculty members' research interests, the number of graduate students that they oversee. We look at 3 of their most recent publications, what type of data is represented in these publications. Does that specific journal provide a research data policy? We look up, do they have any specific funding grants, and were there any requirements for that grant? And then we send them a personalized email. We go to their particular lab and provide this instruction. We do the intro to data management instruction, as well as talk about public discussions of science, research on social media, and one of the biggest or things that faculty like us to talk about is when we do a risk assessment activity, where basically we ask them, if you couldn't find the data, if you couldn't access it, or if you lost it on the server, what would be the issue? Or would that cause a state of panic? And allowing them to go through the steps to provide how they will handle that should that ever happen, or how they handled it in the past. We also do research workflow workshops. And also on the slide to the right, you'll see that's the link for the Illinois Data Bank and all the resources and handouts that we provide and more information about the data repository. Lastly, I think when it comes to the challenges that we face, some of the challenges are indicated by the researchers' responses when they state that they have issues with long-term preservation, with the fact that the formats of the data changes. So if you can access it today, will you really be able to access it tomorrow? Other issues that they express are also within the library, because as librarians, sometimes it feels as if we are outside of the scope of providing data management preservation services. And when I say that, I mean they don't necessarily use us for that. They're used to the fact that we're librarians and we collect data and we keep all their stuff. But when you move past that paradigm to providing services, some of them, they just don't see you that way. There are other issues where some feel that the library is behind on providing research data services. In those cases, I think it's dependent upon your institution. My personal belief, not for the University of Illinois, just want to say that, that it is that you should manage your research data, whether you have the grant or not. And sometimes I think with institutions, you have to start where you are and use what you have. So for some people, that will be only providing data management instruction. For other people, it will be adding other services. So it just depends on where you are and what you can do, and doing the best that you can with what you have. Other issues, I think, are our communication, because sometimes when I was talking to researchers and using words like repository or metadata, they had no idea what I was talking about, or data curation, even though they do it. So it was often trying to figure out how they say it, what they're talking about, trying to understand what they're doing and relate the conversation, not necessarily so I can help them, but so that their needs are being met. I'm not offended if they're not interested in using our services, or even if I can assist them, but I do want them to get the help that they need for the challenges that they mentioned. Other issues that I can think of are, we're interested in finding out how do you really measure the usefulness of the instruction that we provide. I've often asked Heidi, our director of the Research Data Services, is this a one and done thing? I mean, after you've given 5 to 6 presentations to material science and aerospace faculty, you know, do you measure and come back in 6 months, in 3 months, so they can say, okay, I do know how to organize this data, I do know how to describe my data? Or looking at our institutional repository, when we look at what we actually have, the question of, is that data? And the fact that sometimes, because data cannot be defined, and the policy of institutional repository is we take everything, is that really a good policy? And how can we look at how they use it in the institutional repository and compare that to our actual uses for data repository? What lessons can we learn? How can we better meet their needs? She was talking about the annual report that she gave to the Office of Vice Chancellor Research, where someone said, well, yes, we have 50 downloads, that's great. Should there be more? Will there be more? The differences of the fact that with the Illinois Data Bank, we have an actual definitive policy that says we keep this data for 5 years. After that, I'm not sure. They have to reassess what they'll do, but how does that affect research, and what should our discussion be? Unfortunately, I don't have answers to these issues, but I do think working with others will provide continuing solutions. Thank you so much for your time.
Thank you very much. Thank you very much for those presentations. So I do believe we have some time for questions. So I will recommend, there may be microphones going around. I think there may be microphones set up. And if there are any questions, people can address the panel.
I think it was on.
It is. So this is halfway between a comment and a question. I, at this point in my life, am in administration. Most of the discussions about storage, when we do I'm Sharon Geva from the University of Michigan. We believe in collaboration to solve these problems. So library, campus IT, I'm from the Vice President of Research. we have these discussions, and we're administrators, so it degenerates very quickly to who's going to pay and how much. But as I sit there watching these discussions, I'm noting that the people from the library are talking about archiving, the people from campus IT are talking about archiving, I'm talking about archiving. We are not talking about the same thing. So there's two issues here. One of them is how long are we talking about? And it's okay to have varying timescales, and that applies to reproducibility as well. It is fine to have that. The other one is who are the audiences for these things, or who are the consumers for all this data management that we're doing. And I feel like these discussions don't get to the top because we're usually putting out fires, we're usually trying to meet requirements. You know, it's 2 days before a proposal is being submitted, so we're trying to help with data management plans, but we're not thinking out these higher philosophical points. So there's a question in there somewhere, or two questions.
So I think that Sharon has reflected the general question about the various parts, in some senses, what the panel represents. Are there examples of strategies that have worked so far, or do the panel members have ideas about how to improve the communication with parts of the campus and also funding agencies and the greater community? So if anyone has comments, I believe those mics should be live if anyone wants to
start. I think we need to take a step back. And I think the administration of universities and journals have to realize that data storage and management and computing should be viewed as a utility, not anymore as something that each researcher pays for, which is the current state of affairs. I think the moment we recognize that, the moment we see data storage and management and curation as the same footing as air conditioning, power, lighting, we're going to make a lot of progress. And then we can start worrying about infrastructure as opposed to, who needs what. The moment we can put the infrastructure in place to manage this data, exploit it, extract it, the conversation changes, and we can focus on all of these questions that you're raising, which so far hasn't been the case, in my view.
Any other perspectives from the panel? Okay, I think there are some more questions out there. Someone has the microphone?
I'm Kate Doy. I'm from the University of Maryland Libraries, and my question is somewhat similar, and my experiences have been somewhat similar as well in terms of trying to break down these sort of cross-divisional silos that we kind of see between research, IT, libraries, and bringing everybody to the table to talk about this. And so I think my main question for the panel is, what would you perceive as more or less the minimum viable product? Because I'm at a state institution where my budget is getting smaller every year, and where it is unlikely and where it's going to be challenging that I can roll out or help roll out a sort of comprehensive data management program. So what would be, minimum, I guess, to be able to support our researcher needs? And how do you perceive that, and how do we move towards that?
Anyone want to take that on?
Yeah, but I'll let somebody else speak first.
Yeah.
Go for it.
I guess for me, I think minimal, often what you see people do is they focus on data management instruction if they have someone that can do that, or they focus on data management plans. Those are generally the first two places that people actually start, because I definitely understand about budget constraints and the resources that are needed to provide that, but that's an idea.
Just, I guess, one more note. In addition to the instruction, some things that are happening across Louisiana, one thing is collaboration. We have a lot of state-funded institutions, and the funding has been reduced drastically. So there really is a need for collaboration across the institutions. And since we now have the computational infrastructure, the Louisiana Optical Network Initiative, we also now need to collaborate on what's going to be a good storage mechanism across the state, and then use that as a form of revenue generation. once we start building up such a structure. We have some things in place now, but we need to make it more robust. Once we start doing that, we can start being self-sufficient and have a sustainable, work toward a sustainable plan of action for data storage and management.
So I'll give you the faculty perspective now. I think at a minimum, every paper that we publish in the scientific literature, the data for those papers should be stored. I think a conversation has to take place between the journals that sell that content and the universities which produce that content, but somebody has to store all of those data. And I think if you think about cost, an argument can be made that it takes us 1 millimeter cubic of space to store data that used to require a room the size of this one to store. So it should be a lot cheaper now. What we don't have is the software and the culture to store and manage all of those data. Once we decide we're going to do it, it shouldn't be that expensive. And we need to convince our university administrations that, yeah, there's a first investment that you need to make, but in the future, it will be cheaper. Then we also need to tell them and remind everyone about all of the things that we're not doing by being obsolete in the way we manage data. An argument can be made that it is perhaps equally important to store and manage unsuccessful data, results of unsuccessful experiments, because we learn a lot from them, and they're nowhere to be found.
Preston, did you?
Yeah, just to kind of follow up on that, there are some conversations that have happened at Purdue about how to institutionalize the process of putting your data in the repository, your final paper, or like being able to click on the figure and see the source data that generates that, so the student doesn't have to sit there and measure it out and try to get what the data produces that. We do a good job today with making sure that happens from the funding agency's perspective, with the mandates there. But what's not in place, and there are faculty on our campus that are advocating that what needs to happen, is that the graduate students in the production of their dissertations are not necessarily consistently being get some feedback there, are not consistently doing that same data management. Should the thesis deposit process also encourage them to deposit their thesis, put it in the institutional repository, and make that a part of their ingrained habit from their very early days as a scholar, as a PhD student, which is not currently happening today.
Okay, I'd like to get permission from our MC. Do we have another time for another question or two? Okay.
I just have, I'm from AWS. Just a quick comment. I think I appreciate your comment where said the data, you have to understand, at least the archival part, should be more like a utility. In AWS, we store data for 1 year, 3 years, 10 years, 100 years. 100 years. We have a large contract with 180 years with the commercial sector. So for library and other cases, I think and it's, to be honest, the programs we have is such that if you store 100 years, it's much more cheaper than if you store for 10 years or something. Because people worked out the economical model, people worked out the unit calculation. So I think the community start thinking a little bit into those directions, that how do we use this more like a utility or like a service. There are various modes to do that. I had several discussions with various universities where some people say, well, if you have a fund, you have a X amount of overhead, right? If you get a funding from a federal agency, you have X amount of overhead. If you only take 3% of the overhead out of that and invest that 3% on the archival, I will archive all your data of your research for next 20 years. Yeah. If you only give 2 to 3% or 5%, I'm just making up number here, that may solve the problem. But we have to start thinking along those lines, that research data is the data, not only the curation, but the preservation should be part of the whole package.
Yes, I think that the community has, in past years, there has been a little bit of discussion about that and the sustainability. Many of us at our institutions struggle with the right, the right people to contact, the right financial models. Again, is there any comment from the panel about these kind of sustainable financial models and how we arrive at them for very long-term storage? Very long-term, yeah.
Well, so for the archival storage, so and this is kind of along with Sharon's observation about, how people use the word archive, and so I'll be clear as to what archive I'm talking about here. I'm talking about like from the IT guy's perspective, storage that you have people, write once, read never, which is different from the librarian's notion of archival. So with that disclaimer, we've struggled with our HPSS system over the last several years. As we saw the graph there, you can probably imagine why. We've historically funded that just through general funds from our Chief Information Officer's office. So now we're having to figure out a way to insert a cost model onto something that's been in use for 20 years on our campus. So people are accustomed to not having to pay for that, but we're going to have to figure out a way to make it that they pay for something. Maybe it's when they're at a large scale, half a petabyte or a petabyte of data, you pay this much. But you guys who are over here in the noise, maybe you don't have to pay for something like that. We have also made proposals to our administration that perhaps the overhead solution is one thing, or there's a recurring allocation set up from somewhere to help subsidize that. But we don't have the answer. It sounds like nobody has a great answer either, so I don't feel so bad.
Any other comments from the panel?
Yes. So one of the things that's also changing at the same time is that we're reaching a point where data that we used to store, because it was very difficult to compute, doesn't need to store anymore because it's cheaper to compute now. So as long as we store the source code, so that balance, I think, is going to continue shifting in unexpected ways. And then back to the question about being at a state university. I used to be at a state university also. And about 15 years ago, the state built a new building at the University of Wisconsin. And the offices were about half the size that we used to have. And they told us, yeah, they should be half the size because you don't need to store books and papers and all that stuff anymore. This is the digital world. So we all said, all right, can't argue with that. And what they didn't give us was the storage and the infrastructure to store the data. So now it's time to argue back and said, well, look at all this data, where do we put it? If we want to be competitive, we need to put all of those infrastructure and mechanisms in place to be actors in the new world.
So I think we have time for one more question.
So this is Shelley Stalin from the American Geophysical Union. So I come from the journal community as well as the association community. And we do see a real big challenge with our researchers and our students in having those data management skills that you've all talked about, and getting the proper training and having the tools and the infrastructure. So I was wondering if you could please speak on that. The journal community, especially within the Earth and Space Sciences, is moving very quickly towards requiring that data being submitted. We're actually working on that right now. And it won't be very long before it's a mandatory thing. And I'm talking 18 to 24 months. How can we help this community be ready for that moment? Because it's right there on the horizon.
Krista, you mentioned about training. And do you have any more comments? Maybe the only scalable way is to train the trainers, so to speak, or instill in various research communities. I'm curious.
Right. Was your statement, you were saying the AGU was basically going to require the data, is that what you were saying? Right. In our actual instruction program, we do have a portion of the instruction where we talk about the journal data, the journal publication-specific policy as it relates to data and just sharing that information that is not just limited to something that's funding agency or that we're being an enforcer, but this is something that you can see with the specific journal publication. Most recently, a conversation was about Elsevier and the Carbon Journal, Science Advances, Nature's Policy. So we do make that information available to them. We do an instructional seminar that focuses on data sharing as well as data documentation and things to consider with publishing, not just for Elsevier, but we also have in the engineering library, IEEE comes out as well to discuss that.
Any other comments from the panel at this point?
Yeah, I think two conversations have to take place. One between journals and universities, where universities are going to tell you as the publishing community, we're paying for subscriptions, we're paying money for all of this, and now you want us to store your data that you're selling? So a dialogue has to take place to see who owns what and who takes responsibility for what. And then the other conversation has to be between the librarians, who are the masters of understanding how to store and archive data, and the research computing specialists, who can create the tools that we need, that do not exist now, to store all this data and make it available. The moment that happens, we're going to be able to move forward better.
Okay, great. And I think that this workshop, like some other workshops, are very rare in that the mix of people does include people from various parts, and hopefully events like this force us to discuss these very challenging problems. So please join me in thanking the panel.
Okay, we are about to head into a break, but I would like to make one announcement. When we come back, we have two topics before lunch, one of which is our first table-level discussion session. So when you return from the break, please take a look at the back of your name badge. There are table assignments for each of the breakout sessions. When you come back, you are not free to sit wherever you want. Please sit at the table assigned to you for the discussion section. And while you're waiting for things to get started, if you're sitting at your table, please start thinking about Barali's suggestion. We need a scribe for every table. And I will go around personally making sure we have an assigned scribe for each of those groups. So we are going to do a power break now. We're cutting down our break from 30 minutes to 15 minutes. So please, if we could be back in this room at 11:05. Thank you so much.